So folks, in this section, the first thing we're going to look at is the tangent plane to a surface. So first of all, let's give ourselves some intuition for this. So here, in this case, we've got some sort of surface. And when we talk about a tangent plane, what we mean is a plane that approximates that surface at a point that we're interested in. And so the visualization for that is that if you take a smooth surface, and we'll talk about that in just a second, but if you take a smooth surface and you zoom in on it, notice that if I look at a segment of that surface, that looks flatter. And as I zoom in even further, that segment of the surface will look flatter and flatter. And that is true as long as the surface is smooth. And so what we're after then is coming up with an equation of that tangent plane that will allow us to approximate the surface at that point. So the next thing I want to comment on is when will we be able to find a tangent plane? And to kind of remind ourselves of the one variable case is, in one variable, we were trying to find the equation of a tangent line. And notice that as long as the curve is smooth, we can go ahead and find a tangent line there. But notice that if we have some sort of cusp, or there are various ways that we could have a continuous function that wasn't differentiable at a point, well, then we wouldn't be able to fit a tangent line to it. The same thing is going to be similar for our surfaces, that as long as we're able to compute as long as a function is differentiable at a point, we'll be able to compute the tangent plane. And if it's not differentiable at a point, say like this one up here, then it would be impossible to, no matter how you try to affix a plane to approximate the curve there, there's no way that if you do this procedure of zooming in closer and closer and closer, that you'll be able to come up with a plane that approximates the surface at that point. So without going into any further detail for this first discussion, let's go ahead and take a look at what we mean by a tangent plane. Well, one way to look at it, and there's many ways we could look at it, is to say, let's focus in on this point and let's talk about constructing a tangent plane at that point. And so we could imagine a curve that's along this surface that passes through that point where we want to construct the tangent plane. Well, if we have some sort of parameterization for this curve, so here, we've got x of t and y of t, and then z of t is going to be fixed based upon our choice of parameterization for x and y. But if we have some sort of parameterization for this curve, we can then talk about computing the tangent vector of that curve at our point of interest. And so once we've got a tangent vector, then we can think about a normal vector to that, which is going to end up being our gradient. And we'll derive that in class, but notice what we're showing here is that no matter what curve you take through this point, each time we end up with some tangent vector, and the collection of all those tangent vectors forms the tangent plane. And it turns out, just like we've said before, that a plane is completely described by its normal vector and the set of all vectors in that plane passing through a point. We can come up with the normal vector to the tangent plane by simply evaluating the gradient of our surface at P0. Now, this works as long as our surface is described as some slice of R4, and we'll talk about that more in class. But for right now, what I want you to take from this is our goal is to come up with a plane that approximates a surface at a point. And to do so, we're going to think of all of the tangent vectors to the surface at a particular point. That collection of tangent vectors is going to give us our plane, and its normal vector is related to the gradient of some version of that surface. So let's leave it there, and in the next video, we'll talk about actually computing this tangent plane, and we'll give its definition.